This video covers the relationship between electric field and potential. Now, up until now, we've looked at simple situations with potential and electric field, but now we're going to look at a different relationship. That is, the electric field is equal to the derivative of electric potential with respect to position. Again, you do have a negative here. Remember that this can easily be restated in integral form, where potential, or potential difference, is equal to the negative integral of electric field with respect to position. Again, we've seen this equation already derived before. We just hadn't derived it. We use this equation for parallel charged plates, where our electric field is going to be constant, so we can pull that out of our integral, and we are changing with respect to position, so we have our d there. Remember that we still have that negative, but this just tells us the direction of the electric field. Same thing, we can apply this equation, but instead of using uniform parallel charge plates, we're going to be using a point charge, where electric field is equal to kq over r squared. Now, if we put that into our equation, k and q are going to be constant, so all we are taking the integral of is 1 over r squared with respect to position. Now our limits are going to be from infinity to r. So we're getting a charge, or we're finding the potential difference between some point infinitely far away to some point close at a distance r away. Again, we do have that negative, but if you were to work it out, you still end up with the same equation that we had for electric potential of a point charge. So again, you've seen these equations before. Now remember what these derivatives and integrals actually mean. We can relate them to slopes and areas. So the electric field is a derivative of electric potential, meaning that the electric field is the slope of electric potential versus distance graph, and we'll see examples of those in just a second. Remember that electric potential is the integral of the electric field, meaning that the electric potential is the area under the electric field versus distance graph. So, on the left-hand side, you see a graph of a conductor. Again, we know that outside of our conductor, we have an electric field that decreases with respect to 1 over r squared. And inside my electric field, inside my conductor, I have no electric field. So if we look at that situation and we put in that we have a 0 electric field at the inside of my conductor, what that means is I'm going to have 0 potential difference. That does not mean I have 0 potential. All that means is I have no change in my potential. So the potential I have at the surface of my conductor is the potential I'm going to have all the way through my conductor. In this situation, on the left-hand side, I have an electric field graph of an insulator. Again, we know that inside of my insulator, I do have an electric field that's going to increase linearly as I move from the center outward in the positive direction. So I'm saying from here out, I do have this increase in electric field. And then as we reach our surface of our insulator, my electric field starts to decrease with respect to 1 over r squared. Now, again, if potential is the negative integral of the electric field with respect to position, then we're going to get these curves inside of an insulator for potential. So again, in these examples, we're just going to be taking the derivative or integral depending on the situation. For the first one, the electric potential in a region of space is described by the function below. Determine the magnitude of the electric field at r is equal to 2 meters. So we have our potential function. We know that our electric field is going to be the negative derivative of potential with respect to position. So we need to take the derivative of 4r cubed plus 2r squared plus 3 all over, with respect to position. That's going to give us a negative 12r squared. Make sure you distribute that negative, minus 4r, and then the derivative of constant is 0. Again, this is our electric field function now, but it asks us to evaluate it at r is equal to 2. So if I put in all of my values, I should get an electric field of a negative 56 Newton per Coulomb. But the problem did ask only for magnitude, so it is simply 56. In this last example, the electric field in a region of space is described by the function below. Determine the potential difference between r is equal to 1 meter and r is equal to 4 meters. So, our electric field is equal to 12r squared plus 4r. If we want to solve for our potential difference, we need to take the negative integral of the electric field with respect to position. So that's 12r squared plus 4r. The integral of that gives me 12r cubed over 3 plus 4r squared over 2. And again, just to clean that up, I get 4r cubed plus 2r squared. And I can factor out a 2 if I really, and an r if I really wanted to clean it up even more. Again, our integral is from 1 meter to 4 meters. So if we plug in all of our values, you're going to get a potential difference of negative 282 volts. But again, potential difference is relative to a reference point. So really, a potential difference of 282 would be sufficient. And a way to better illustrate that is, let's say that you have two parallel plates, and at one point you have 5 volts at the positive plate, and at the negative plate you're calling this your 0 point. You have 0 volts. Your potential difference between these would simply be 5 volts. But you could go further to say, to compare two different points. Let's say you're going from point A to point B. Well, if you go from point A to point B, then yes, you have a negative potential of 5 volts. But if you go from point C to point D, then you have a potential difference of positive 5 volts. So again, if it's asking for potential difference, really you want to focus on the magnitude of it and then look at whether it's going to be increasing or decreasing depending on how you are moving. Another way to say this is that our electric field is always going to go from positive to negative. But you can see the relationship that the electric field is always going to go from high potential to low potential. That's true even when you have a situation where you have, let's say, a negative 2 volts, 0 volts, and a positive 2 volt. Well, if volt is a scalar or potential is a scalar, that means my electric field is still going to go from highest value to lowest. And remember that it always has to be perpendicular to your equipotential lines, like we talked about in our last video.